The periodic table is a valuable list of all known elements organized so that groups of elements with similar characteristics are arranged together. The periodic table evolved over many years, and it resulted from the careful observations and experiments of many brilliant scientists in the 19th century. Most prominent of those scientists was Russian chemist Dmitry Mendeleev, whose arrangement in 1869 of 60 known elements into groups having similar properties became the precursor of modern periodic table. An example of a periodic table is shown here. As you can see, periodic table consists of multiple groups. In fact, there are 18 vertical columns, as you can see from here to here, and we have multiple horizontal rows. The vertical columns are known as groups. So there are 18 groups, and the horizontal rows are known as periods. Elements that appear within the same column on the periodic table are known as a group or family of elements. For example, this entire list of elements which appear in the first column are known as alkali metals. So this is a one group of elements. Similarly, the second group right next to it is 2A group. The name of these group of metals is known as alkaline earth metals. All the metals uh, in the middle of the periodic table from here to here, this section, all of these metals are known as transition metals. If you notice carefully, as we go from left to right in a horizontal row, the atomic number goes up by 1. So for example, potassium is 19, next is 20, then 21, and so on. However, if you notice here, so starting from this period, first element cesium is 55, right? To the right of cesium we have barium 56, and then we have lanthanum 57, but after 57 the next one is 72. So why there is a gap? The gap is because in this small space we have list of 14 elements missing, so we cannot put those 14 elements right there. So it's kind of like an insert which is represented outside. So all of these elements, these 14, they are supposed to be in this tiny space, and similarly between 89 to 104 in this area. So this is the list. So these two rows of element, these are known as inner transition metals or elements. The group 8A on the right hand side, these group of elements are known as noble gases, and 7A known as halogens. All elements within the same group exhibit similar physical and chemical properties. For example, characteristic physical property of alkaline earth metal, which is group number 2A, is their shiny silvery white appearance and soft flexible consistency. For example, all magnesium, calcium, beryllium, strontium, all of these metals are silvery white and soft. Another example of a similar property within the group is noble gases. The property is that all of these elements are gases, and they do not generally react with other elements, and they are found in elemental state. Elemental state means that they are found as individual atoms. As mentioned earlier, The elements within the same group have similar properties. The group 1A elements are known as alkali metals, group 2A are known as alkaline earth metals, group 7A are known as halogens, and group 8A known as noble gases. A row of element in periodic table is referred to as period. For example, in this figure, fourth period is shown here, and in fourth period we have elements such as potassium, calcium, selenium, titanium, vanadium, chromium, manganese, iron, cobalt, and so on. The first period of elements contain only two elements, which is hydrogen and helium, and uh, second and third period element contain eight elements. Recently, the seventh period was completed. The final four elements were discovered in last few years, and their official name were given in 2016. Another thing to notice here is this zigzag line in this section of the periodic table. What's the meaning of this zigzag line? This line represents a divide between in the periodic table. The elements on the left of this line, on this side, all of these elements except the first one, so all of these elements to the left of this zigzag line are metals, and all the elements on the right side, these are non-metals. There are some elements which lie directly on this zigzag diagonal, so these elements are somewhere in the middle of metals and non-metals, so these elements are known as metalloids. All the elements which are shown in blue in color are metals, and the yellowish orange color elements are non-metals, and all pink colored elements are metalloids. Generally, metals and nonmetals have very different physical and chemical properties. Metalloids have characteristics of both metals and nonmetals. For example, metals are shiny, they exist as solid at room temperature. There is one exception, so that exception is mercury. So mercury is liquid at room temperature. All other metals are solid at room temperature. Metals are good conductor of heat and good conductor of electricity, and they are flexible, they are malleable. On the other hand, non-metals are not shiny, they are dull, they do not conduct electricity, they do not conduct heat. They are some of them are either gases, liquids, or they are even solids. So their properties are exactly opposite of metals. Metalloids, on the other hand, their properties are somewhere in the middle of metals and non-metals. For example, silicon. Silicon is shiny, but at the same time, it does not conduct heat. It does conduct electricity little bit. It doesn't conduct a lot like metals, but it's not an insulator like non-metals. So the point is that metalloids have properties in the middle of metals and non-metals. This table shows the comparison of some of the physical properties of metals and nonmetals. As I explained earlier, metals are shiny, but nonmetals are dull. Metals are generally solids at room temperature. Nonmetals can be solid, such as carbon, phosphorus, and sulfur. There are some nonmetals which are gases, for example, oxygen, chlorine, nitrogen. Metals are good conductor of electricity. Non-metals are not, metals are flexible, non-metals are brittle. Elements with an important role in biochemistry and medicine are highlighted in this periodic table. The 6 building block elements represent the atoms that combine to form compounds found in living organisms. These elements are carbon, uh, nitrogen, oxygen, and hydrogen, up to some level phosphorus and sulfur. There are 7 macronutrients. These are shown in orange boxes, such as here. Macronutrients are those nutrients which are required in quantities greater than 100 milligrams per day. The examples of macronutrients are sodium, potassium, magnesium, calcium, phosphorus, sulfur, and chlorine. Phosphorus and sulfur are both macronutrients as well as building block elements. There are 12 micronutrient elements. These elements are shown in yellow boxes, such as here. Micronutrients are those elements which are required in quantities less than 100 milligrams per day. The role of all these macro and micronutrients will be studied in chapter number 17 at the end of this book. Let's take a look at this example problem. State group number and common name of these elements. First is beryllium. Beryllium, the symbol for beryllium is Be, and it is present in here. So group number is 2A. So Be is present in group 2A, and the common name of group 2A metals is alkaline earth metal. B, iodine. So iodine is here, so that is iodine. Iodine is present in group 7A, so its group number is 7A, and the common name of this group is halogens. So iodine is a halogen. Next is argon. Symbol for argon is Ar. It's present in group 8A, so argon is 8A, and the common name is noble gas. The final one is nitrogen. Nitrogen is present in group 5A, and there is no common name for nitrogen elements. Provide the element name and atomic symbol for each element described. So A, group 2A metal in period 5. So this is 2A group, and we need to look at period 5. That's period 1, period 2, period 3, period 4, and period 5. So period 5 and group 2A, the metal is Sr, and Sr, the name of this metal is strontium. Halogen in period 3. So we know that halogens are group 7A, and in third period. So third period is this one. So halogen in third period is number 17. So it's Cl, and it stands for chlorine. The last problem is transition metal in period 4 with 2 more protons than calcium. So 2 more proton means its atomic number is 2 more than calcium. So calcium is number 20. This is calcium number 20. So calcium is 20. So 2 more than calcium means 22. So 22 is this one. So the answer is titanium. Ti is the symbol. The physical and chemical properties of an element will largely depend on the arrangement of electrons in an atom. The model scientists use to describe the electron arrangement in an atom is based on the theory developed in early 20th century by Einstein and other famous scientists, and this theory is known as quantum mechanical model, or in general quantum mechanics. Before quantum mechanics was developed, it was believed that atoms contain or consist of a nucleus, and nucleus contains protons and neutrons, and around the nucleus electrons move in fixed uh, paths, and these paths are known as orbits. So for example, this is the first orbit, second orbit, and there might be electrons in different orbits. This model was similar to solar planetary model, where in the center we have sun and then planets rotate around the sun. But later it was found that this model is not the accurate representation of the structure of atom. Electrons are not in present in orbits. So this model was proven wrong. Now, according to the newest model, which is quantum mechanics, electrons are uh, are arranged around the nucleus in certain allowed energy levels. So now we don't have orbits, we have energy levels around the nucleus, and these energy levels are represented by the symbol n. According to quantum mechanics, the allowed energy levels in an atom increase in steps, and these steps are called quantas. For example, if the nucleus is somewhere here, and around the nucleus this is the first energy level, then that's the second energy level, and that's the third energy level, and fourth energy level, and so on. So these each level represent a step in energy. So going from one level to the next level, you would need some energy. That's why what we call them as quantized energy level. Electron energy levels are identified by numbers. For example, n equals 1, and 2, and 3, and 4. The lowest number, which is n equals 1, is closest to the nucleus. Electrons are arranged in these energy level. There are some rules which state that how many electrons can be on any particular energy level. Any electron which is on the first level, for example, this electron in case of hydrogen, will be the closest to the nucleus. As electrons go to higher levels, for example, in lithium, this electron is on second energy level. So it's farther away from the nucleus. Electrons which are closer to the nucleus, for example, all the electrons on level number 1 are more stable, and hence they have lower energy. And electrons which are farther away from the nucleus, such as this one, so these electrons will have higher energy and they will be unstable. This situation or condition can be similar to a ball placed on the bottom of the hill and farther up the hill. Any ball which is placed farther up the hill will have higher potential energy, so hence it will be more unstable rather than the balls placed at the bottom of the hills. Each energy level has a limit of electrons which it can hold, and that condition can be summarized by this formula. So maximum number of electrons on any level is equals to 2n squared, where n is the number of level. For example, if we want to calculate how many electrons can be on the first level, so n equals 1 for first level, so maximum number of electrons will be 2 times 1 square, which is 2. So it means on the first level, maximum number of electrons which can be present is 2. So first level cannot hold more than 2 electrons. So if an element has more than 2 electrons, first 2 electrons will be on the first level, and then remaining electron has to go to the next level. So as explained earlier, the formula to calculate the maximum number of electrons on any energy level is equals to 2n square. Using this formula, we can calculate that first level contains maximum of 2 electrons, second level can hold maximum of 8, and third level can hold a maximum of 18 electrons. The electrons in the highest energy level of an atom are known as valence electrons. For example, this figure represents the energy levels of hydrogen, lithium, sodium, and potassium. As you can see, in case of hydrogen, it has only one electron, and in previous slide we learned that first energy level can hold a maximum of 2 electrons, so this one electron will stay in the first energy level. Please remember, electrons want to be at as lowest energy level as possible. However, when an energy level reaches its maximum capacity, then the remaining electron has to move to the higher energy level. For example, in case of lithium, it has 3 electrons. Only 2 electrons can stay on the first level, therefore third electron has to go on the second energy level. Now, the electron on the highest energy level is known as valence electron. In case of hydrogen, the first energy level is the highest. So hydrogen has one electron in its highest energy level, so it has one valence electron. Similarly, in case of lithium, level 2 becomes the highest energy level, and it contains only one electron. Therefore, lithium also have one valence electron. All other electrons are known as inner electrons, or they are also known as core electrons. So any electron which is not valence will be a core electron. Similarly, the valence electrons of sodium and potassium are shown here. In case of both sodium and potassium, they have one valence electron because that's the highest, that's the electron present in the highest energy level. If you notice, one particular thing here is that all these elements belong to 1A group, and all of these elements has one valence electron. So this is a similarity between all these elements within the same group. And another similarity is that if the elements are from 1A, they will have one valence electron. So this is easy way of knowing how many valence electrons are present in any particular atom. All you need to know is that in which group that element lies, and then from that you can tell how many valence electrons that particular atom will have. Let's look at some of the elements of group 2A. So as you notice that they are from group 2A, and all of these elements such as beryllium, magnesium, calcium, they all have two valence electrons, or in other words, they have two electrons in their highest shell. So we can now generalize that whatever is the group number, the same number of valence electrons will be present in all the elements present in that group. One thing to remember is that this logic only works for the main group elements, which means that it only works for the groups who have the names 1A, 2A, and 3A, and so on. This logic does not work for transition metals. Let's review one more time about valence electrons. Valence electrons are those electrons which are present in the highest energy shell of an atom, and it is easy to figure out how many valence electron any particular element has. All we need to know is the group number. So for example, this is 1A, this group is 2A, and this group similarly 3A, 4A, 5A, 6A, 7A, and 8A. So all elements in group 1A has one valence electron. So it means all of these elements in this group, they have one valence electron. And similarly, any element in this group, so this group is 5A, so therefore they will have 5 valence electrons. So we can extend this logic. Group 2A element has 2 valence electrons. Group 3A to 7A has 3 to 7 valence electrons. And finally, the last group, 8A. So all of these elements have 8 valence electrons. So valence electrons are electrons found in the highest energy level. In general, atoms with valence electrons in higher energy levels are larger because their electron clouds extend farther from the nucleus. For example, lithium atom with its one valence electron in an N2. So lithium, so this is N1 and N2. So lithium has, so valence electron is in N2. So lithium has a smaller diameter than potassium atom because potassium atom has valence electron in fourth energy level. So it has so N equal 4. This is 3. That's 2, and that's 1. So this is potassium. So as you can say, potassium atom is much larger. So nucleus is somewhere here in the middle. So potassium is much larger than lithium. In next chapter, we will learn how valence electrons are involved when atoms join together to form compounds such as water and sodium chloride. In the next part of this chapter, we will learn about isotopes and radioactive isotopes, and in that section also we'll learn how valence electrons are involved. Periodicity is defined as a repeating pattern found in the periodic table. In elements within the same group of a periodic table, the physical and chemical properties are quite similar, and the similarity or in the physical and chemical property, there's a repeating pattern, so that's why it's called periodicity. And periodicity also depends on the electron arrangement in the energy levels or shells. Let's take a look at some problems. So firstly, how many valence electrons are present in barium? So in order to find valence electron, first we need to know in which group barium is present. So symbol for barium is Ba, and barium is number 56. It is here. So if we look at it, so this group number is 2A. So 2A means it has 2 valence electrons. For carbon, symbol for carbon is C, and carbon is present in this group, and this is 3A, and carbon is present in group number 4A. Therefore carbon has 4 valence electrons. See, it's really easy to find how many valence electrons any element has. Just look at the group number. Let's complete this table. I'll start with the row number 1. So atomic symbol is given He, and we know that He is a symbol for helium. Helium is a noble gas, and it's present here. number 2 here. And now we need to know what is the atomic number, and we can see the atomic number given in that box is 2, so it has 2 atomic number. Group number, I'm gonna write all the group numbers, so that's starting from this side: 1a, 2a, then this is 3a, 4a, 5a, 6a, 7a, and 8a. So as we can see, helium is present in group number 8a. Period. So this is first period, that's second period, and so on. We don't have to go farther down because helium is in the first period. Number of electrons, number of n equals 1 electron. So number of electrons in helium neutral atom is same as protons, and we know it has 2 protons, and so it has 2 electrons, so answer is 2. So n equals 1, n equals 2, and n equals 3. These are the various energy levels, and helium has total of 2 electrons, so all of those 2 electrons can be in the shell number 1 because shell number 1 can hold a maximum of 2. Okay, so that's 2. Number of n equals 2 electrons. Helium does not have any more electrons, so and second and third shell are empty, so answer is 0. Third shell is also 0. Okay, let's complete the second row. Second row, not much information is given about the atomic number or the symbol or anything else. Only thing we know is that this element has 2 electrons in the first shell, so that's unknown. So n equals 1 hold 2 electrons, n equals 2 hold 8 electrons, 1 2 3 4 5 6 7 8, and n equals 3 also hold 8 electrons. Now we need to figure out what is this element. So let's count the total number of electrons. So total number of electrons is, so 8 here and 8 here, so 8 plus 8 plus 2, so total number of electrons is 18. Okay. So because it's a neutral element, and in neutral element or neutral atom, number of electrons is equal to number of protons. So if it has 18 electrons, so therefore number of protons is also equals to 18. If number of protons is equal to 18, we also learn that atomic number is same as number of protons. So atomic number of this element is also 18. Now, from the atomic number 18, we can figure out what is this element. So atomic number 18, so symbol for this element is Ar. All right, and the name for this element is argon. It's another noble gas, and argon, we can see it's also present in group number 8a, and argon is present in period number 3. And now we are done with the table.